Now, this is actually two lectures that I did in Switzerland, and it's designed to be 3 hours long, to one and a half hour segments. So we probably won't get through it all, but I don't think that's too much. I want you to give a guess. I may ask you to interact now. Oops, that's not enough. That's too much. What do you think that is? This is not a curiosity. Anyone recognize it? Probably not, because it's maybe before your time. I don't know. Time flies, isn't it? So let me give you a hint. That's how many transistors it contains. CPU. And if I highlight that, does that tell you? It really does have that number of transistors. Someone counted them, but it's a 46. So I'm just showing that to make the point that we're not going to talk about anything like that. That'll be a relief. Indeed, some of the circuits I'll be talking about will only use one transistor, so it's a different world altogether, and of course, it's the multi-dimensional world of analog. I'll talk about that thing that's showing there later in the day. But noise, of course, has always been important, but it was not sort of at the top of the list of considerations in many of the older books. If you read any of the older books on electronics, noise is dismissed rather briefly. But with the advent of radar, in particular, the ability to pull a signal out of a noisy background became more and more important. So that's a radar indicator unit from World War II. And nowadays, of course, the clever manipulation of coding in communications channels is also designed as with error correction as one of the ways to mitigate against noise. But for all of that, noise remains just as fundamental and just as persistent and problematical as it ever has been. So we're going to talk a bit about the fundamental sources of noise, because I think that's more important perhaps than a lot of discussion of circuit noise. We'll try a little bit of that later. But sometimes you see in books, in chapters on noise, rather long equations, and I feel you lose the intuitive grasp of what it's all about. So I'm going to try to get down to basics, and I hope I won't be preaching to the choir. So this is our objectives, to emphasize those fundamental issues and talk about some of the key mechanisms, demonstrate that they're really very much the same thing, and suggest a few ways of minimizing the impact of noise. So it's in two parts. As I said, they're both supposed to be 1.5 hour segments, but we'll sort of ignore that. We won't have a brief pause for copy and reflection, unless you want one. So we'll get there in time. So let's talk a bit about some of the basic ways of first of all, before we talk about where noise comes from and some of those basic mechanisms, we need to talk a bit about how we're going to quantify and measure noise and so on. As you understand, most noise exhibits a probability density function. That's its amplitude function, taken as a sort of a histogram, that is Gaussian, and this we call white noise. Another way of talking about white noise, of course, is that it is the summation of an infinite number of sinusoids all out of phase. So in talking about noise, we'll talk about NSD, noise spectral density, or voltage noise density. And that has the dimension of volts per hertz, per root hertz, excuse me, I lost my root sign there almost. And similarly for current, of course, it's certainly amps per root hertz. Now, power, of course, is a more important parameter in such applications as radar receivers, as cell phone receivers, because always you're fighting the available signal power, or the available signal power is fighting against the thermal noise floor and other thermal noise mechanisms in the front end of the receiver. So it's usually more important to talk about noise in power terms than in either voltage or current. I mean, you can imagine, just to take a silly example, if you had an electrostatic generator of 100,000 volts that had a fluctuation of a volt on it, so what? It doesn't amount to anything in terms of power, even though it's a very large voltage variation, 1 volt with a rather large variation. So the other thing that, of course, we've got to come to grips with is that because noise is a statistical process, the time over which we average, or the time available for averaging, which we can call the observation bandwidth. Obviously, the longer you conduct an averaging experiment, the less the variance. So it's no surprise that the power in a noise is proportional to bandwidth, directly proportional to bandwidth. But in volts, in voltage noise density, voltage noise spectral density or current noise spectral density, that those noises are proportional to the square root of power, the square root of bandwidth. Excuse me. I hope that made a bit of sense, but we'll get there one slide by one slide. Now, we talk about noise as being white, which means that in an arm-waving way, it has frequency components like to terahertz. But quite clearly, our circuits don't respond up there, and many circuits don't even respond to gigahertz frequency. So the question arises: where does the bandwidth come from? What limits the bandwidth of the circuit? And I use the term inertia because I think it describes best this idea that circuits can't change their state immediately, just like a car can't suddenly start going at 60 miles an hour. So it's the inertial aspects of our circuit that are going to actually define the bandwidth. In a very primitive device, or primitive circuit, such as a bipolar transistor, we're trying to look at, say, the noise at the emitter with the base grounded, or at the drain, at the source with the gate grounded. The bandwidth is entirely determined by the one device, but still the device has inertia, of course. So it's these inertial aspects that are going to determine the noise spectral density. It therefore follows that when we speak of a spot noise, you'll sometimes see, a noise figure of 1 dB at 2.4 gigahertz. Well, this illuminates the practical fact that the noise spectral density measured in a 1 hertz bandwidth, that's per root hertz, or in a narrow bandwidth, actually varies across the frequency band. If we look at the total integrated noise, it's defined by the bandwidth of the entire amplifier or system mix or whatever it might be, but usually we're operating such things as radio receivers at single frequencies with rather narrow bandwidths. So noise figure is sometimes a bit misleading because it's sometimes suggested. I've seen ads for transistors that say noise figure of 1 dB, and it doesn't mean a thing because it all depends upon how you use the device. What they really mean is that under the best conditions, you can get this thing to work down, that far. So there is this difference between integrated RMS noise and measurement at a spot frequency with a 1 hertz bandwidth. So what I'm saying here is that there are two factors overlapping. One is the spectral quality of the noise source itself, and the other, of course, is the transfer function of the. Let's see if I use this big stick here. The transfer function of the amplifier or filter or whatever it might be that determines the amount of noise power that makes it to the output. So now, when it comes to summing all the noise sources in a circuit, each of the devices contributes some noise. In terms of power, I think it's fairly self-evident that the power simply add up. But again, if we just refer to a noise voltage or a noise current, then the total power is proportional to their magnitude squared. So one must add up these individual noise components, such as the input noise of an amplifier and the noise of a following amplifier, maybe with a gain term included in there. We've got to square those quantities. Again, much of this is 101, but it's part of the deal here. So that's just a little summary of that. It says there's more. I'm sure you are aware that in simulators such as SPICE, by the way, what simulators do you use here? Would anyone offer a suggestion? The simulation core. Is it SPICE, HSPICE, or something like that? Okay. Well, in looking at noise in standard simulators, it's important to understand that the simulator knows nothing about the stochastic or randomness, real randomness of noise as a process in time. All it does is it says this resistor is 1 k-ohm, therefore it's going to contribute 4.08 nanovolts per hertz. Add that into the summation that it finally does and tells you what the total added up noise is. But it doesn't know what noise really is as a random process. So you've got to be a little bit careful in a number of ways. I wonder, is it possible that the projector get the bottom? I think my picture's too big or something. Doesn't matter. So, as we'll see in just a moment, or as I'm sure you understand already, noise is a process in time that is not often modeled in simulators. However, it can be. And a lot of modern RF simulators accommodate the fact that this is really a process. And our own simulator, which is called ADICE, incorporates something I call TNT, which stands for Transient Noise Test. That is to say, when we do a transient analysis, we stop at every point where the matrix has been solved and we've reached equilibrium at that particular time point, jump out of that process into the noise process, measure the noise at that instant, at some specified frequency, and then pop back into the transient analysis, go to the next time point, and so on. So what you end up with now is a vector which is noise versus time. And I'll show you an example of that in a bit. It's very powerful because I had some trouble convincing the CAD folks we can do this because they said, well, what are the dimensions? I mean, it's meaningless. And I said, well, not really. It's just a comparative tool. Very often when you're designing with a simulator, you're using it just to compare one idea against another. You're sort of making a progression from an initial idea, which looks like it's promising, and you maybe change its topology a bit, you warp it and move it and apply different operating conditions. And you're just really comparing the last set of results with the previous set of results. So if you can look at your noise versus time waveforms, and you can choose whatever frequency you like, and many frequencies, you begin to realize, gosh, there's something going on here that I hadn't thought about. And I'll show you a good example of that in just a moment, well, a few moments anyway. TNT is not too hard to incorporate into any process. If you've got CAD folks here, you might want to try that. It's a very powerful tool. I say at the bottom, this is the reason why I was concerned it wasn't quite visible, is it says all things worth doing must be semi-hard. One of my little axioms. Okay, yes, real noise is a process in time. So, some of these comments are really an answer to some of the people that you may know about, or one at least in the public eye, who has no time for simulators at all. He's a bit of a joke. But he insists that simulators lie, and of course I tell him that people lie. It's an act of commission, not omission. Noise analysis is generally correct, but you have to know your tools. It's like any other tool. You have to know its limitations. So you must use a simulator in a creative mode in these comparative studies. And also, I say, as a platform for gaining insights. I'm a great believer in the acquisition of insights rather than solutions. I mean, the solutions come. I sometimes say of a product development, there are two consequences. One is the product, the IC you can sell, make some money out of, and the other is experience, of course. And which is the more important? Well, the product makes some quick money, but the experience makes money later on. I sound like I'm a profiteer, I'm not, but you know, when you work for a company, it is all about making money, unfortunately. So the experience is very important, and a simulator can teach you, because built into a simulator is hundreds of thousands of person hours of thinking about how devices work, of modeling and so on. In many cases, some of the limitations, if you're using TSMC as a process, or another foundry process, you may find the models are not only pretty primitive and incomplete and not up to date, but the parameterization of those models is also incorrect. I mean, there's two distinctions here. There's the equations that define current transport in a device, and then there are the numbers attached to those equations, the coefficients, if you like, and they can often be very, very far off from the truth. The only way of getting around that is to make your own measurements, or have your own group make the measurements, and we're lucky in having a CAD group that does some very good characterization work. So those are some of the limitations of simulation. When it comes to noise, where we begin to go off the rails a little bit is, first of all, when there's a great deal of nonlinearity in a system, and secondly, when we're working at frequencies which are really at the edge of the inertial limitations of the devices. So, for example, if you're using devices in some amplifier out of 30 gigahertz, in a talk I gave last Wednesday, there was a log amp of that kind. The noise modeling at 30 gigahertz, you better not expect it to be too exact for a lot of rather obvious reasons. It's not totally misleading, but it's not something that you should really hang your hat on. So here's a couple of definitions that are used in noise quantification. Noise factor and noise figure. They're really the same thing. The difference being that noise factor is a simple ratio of the power at system input to the power, the signal noise power, I should say, at the system output. So obviously, if we degrade the denominator by say 60 dBs, then we have a noise factor of noise factor of 2. Now, the noise figure in power terms is simply the value of the NF. And sometimes it's confusing because you'll see NF as a spec, and it's not clear if it's noise factor or noise figure because they sometimes don't bother to put the dB on the end, so watch out for that. This noise figure, it should be defined in dBs. Now, the point I'm making here is that the noise figure isn't a fundamental aspect of the circuit. It's something that arises out of a number of decisions we make about the spot frequency, the operating bias conditions, and circuit temperature, and process technology, and a lot of things like that. Let's see. Yes. Okay. This again, it just makes it almost the same point, but I'm just saying that when you use SPICE and you specify a node at which you want to measure the total accumulated noise or noise at the out node, let's say, it'll have a dimension of volts per root hertz, and it's not a power. So when we make the conversion now from the noise factor, we will use 20 log 10 because we're talking about voltages now. In the previous slide, you may remember we were talking about powers. It will come back, yeah. Symbolized power ratio, and now we're talking about voltages, so we have to use 20 rather than 10. I think that's fairly obvious, I hope. Yeah. Frequently, when you're making noise measurements, you will end up with this is SPICE the same as Ada's plot noise n parenthesis nothing that plot the noise that will be specified in the noise. Well, some of that is due to the source resistance, of course, and it's very easy to calculate the noise figure as simply 20 times the log base 10 of that amount that SPICE tells you, n parenthesis, divided by the noise of the source resistance. And I hope SPICE is the same in this way. Even though you didn't specify the source resistance terminals as nodes for measurement, you can still measure the noise of all the components in the circuit just by specifying their name. So this is all the noise figure is. So it's very easy to do, and you know, as accurate as you generally need. In fact, very accurate. So I want to give a quick example here before we start talking about noise sources of the important difference of termination and matching. Supposing we have a source resistance of Rs, and because it's connected to our system, say by a cable, or because the generator, in order to be calibrated correctly, or in order to operate correctly, as a filter, for example, needs to see the proper termination resistance from its own selfish point of view. But if we do the termination, or if we apply the termination resistor in this fashion, and we can assume the moment the amplifier is just noise-free because it's the resistor we're worried about, you can see that you've divided the signal by 2, but you've checked, and you would make, let's have some equations here. You will change the apparent noise resistance by a factor of 2, because RT and R source are now the same. So instead of say 50 ohms, we've got 25 ohms at this node. So we have the noise of the 25 ohm resistor, which is 3 dBs less than the noise of the the 50 ohm resistor, but the signal is 1/2. So in the end, we'll end up with a factor of √2 in the overall signal-noise ratio. So the noise figure will be 3 dBs in this case. That's the best you can do. Now, 3 dB of a noise figure in, say, a radio situation it would be very good for something like a mixer. It would be very, very good for a mixer, but it wouldn't be so good for an LNA. LNAs generally, low-noise amplifiers for radios, generally have noise figures of about a dB, something like that. So this is not a way of, if this were an antenna, for example, and it had been the power from the antenna, the amount of power it intercepts. By the way, it's very, very tiny. Typically, at the extremity of a cell phone range, we're talking about picowatts of current. And we're trying to fish out picowatts of signal above the noise processes that the circuit has to contend with. So it really is a big challenge. Another thing that's worth mentioning too is that you have to do with bit error rate as a measure of one of the implications of noise is it's going to erode the bit error rate. Well, the ratio between the bit error rate and the noise figure is around about 10 at 12 dBs. It's a rather complicated curve, but if the noise figure is about 12 dB and you can get it down to 11 dB, it will be 10 times better in terms of bit error rate. So it's a big deal, particularly since every communication channel these days is doing it. So, so this is not a very good way of, I was saying if this is the power from the antenna, and this is part of the antenna impedance looking back into it, and the cable impedance, then we'd end up with a hugely inappropriate noise figure. So what do we do about that? Well, first of all, this is something to also mention. I know there are a lot of digressions here. I don't know quite how to do this in any other way, but when you simulate noise over temperature, as I'm sure you do, you're often interested in how bad does this thing get at 120 degrees centigrade or whatever. Well, I was thinking of a little alphabet there, but never mind. The concern here is that the presumption is that the source is at a constant temperature. And it gets quite interesting to ask, what is the noise of an antenna? And in the end, it comes down to the fact the antenna is coupled into free space with an impedance to 300 ohms. So that 300 ohms can be regarded as dissipated, believe it or not. And it acts just like a resistor, eventually after being maybe transformed down to a different impedance. What is the impedance RS? Well, it doesn't vary. Your handset, well, it's quite complicated. In a handset, the antenna is at the temperature the handset's at, which of course had better not be 120 degrees C, it'd be rather a hot phone. But it isn't the antenna heat, it isn't the temperature of the metal that determines the noise, the noise of the antenna. It's the free space it looks out at. In fact, if the antenna happens to be looking out over a city, that noise is aggravated by a lot of the noise coming from the city. So it's kind of a complicated thing. But the point is that in simulation, you want the noise temperature of the source to be constant. Now, as a matter of fact, noise is traditionally specified at 290 degrees Kelvin. But in simulation, you're going to vary it. And the point I'm making here is you better watch out, because the modeling of resistors, if you just take a resistor from the library, includes a temperature behavior of noise in that resistor, which we'll get to a bit later. So if you're sweeping temperature of the source as well as your device, you're seeing a noise figure that's worse than it really might be. It's too bad we're losing a lot of the bottom text here, but that's life. So here's your system, and here is what you want to model. So there's a very simple thing you can do here. And by the way, I told Professor Minch that you're welcome to have these slides, and look them over at your leisure. So if I go too quickly, well, that should help. But anyway, here's something you can do. You use the resistor, the only one you've got not the only, you've got many films, many choices, but they'll still have the temperature behavior of a resistor, and you multiply it by the switch factor. And T degrees C, of course, is being swept in these experiments, but the noise resistance is being kept at a constant, effectively a constant temperature. And so I just show the noise, the source resistance here having this property, then a little voltage control voltage source, just to buffer it, and now you're looking into your system. Now, the one thing that's missing here is that you'd really like to have a noise-free 50 ohms in there. And because the behavior of, we haven't yet modeled the termination aspect. In fact, there is no termination here. But this does work. It's not the whole story, but it's just a reminder that if you want to keep the noise of the source constant, you can actually do that in a very simple way. People who work in radio astronomy, and one of the folks who used to work for me, Roberto, went down to Arecibo, and he works down there on the telescope, like to talk about noise temperature. A very simple translation is from the noise power spectral density of a signal, which is watts per hertz, divided by Boltzmann's constant time of bandwidth. And for example, if we have, what do I say here, a bandwidth of 50 kilohertz and certain other conditions, minus 110 dBm per hertz of noise, then that's an effective noise temperature of 14.5 Kelvin. I don't find a lot of use of noise temperature myself, but as I say, if you work in astronomy, it's a big deal, and you're trying to get your noise temperature of the front end down to the kelvins, a fraction of kelvins even. So let's talk a bit about where noise comes from. It's very much an aspect of the physical universe, and in some ways it's almost mysterious, but not quite. The first point we need to make is that the current flow is a granular process. Yes? I can turn them off if you like, but then that's the next step, unfortunately.
There may be an issue with the slides.
Sorry?
There may be an issue with the slides, I'm not sure. Is that what it's supposed to look like?
The cable is...
Oh, the blue is not very good.
That looks like a salt blue. That's like the blue is great, and the red and the green are bad.
Well, I can even do this, and then maybe I can try it anyway.
No. Do you know the cable?
Yeah, I fear we may have some problems.
Oh, is this supposed to be green on this side too? Yeah. Because I keep it's supposed to be green randomly.
Something's
It's a bad cable.
Yeah.
I'm stepping on a cable down here. Maybe the listeners. This VGA cable is just dangling out here.
Here we go.
Or cable not plugged in. Oh, sure. There is no speaker. Cool. That's a good word game then.
You see what a training in electronics does for you? Now you can maybe have a bit more light. It's still pretty bright. Yeah. We're still on midway.
That's great.
So, we'll be very specific about the granularity current in a moment. These classifications, well, the first two anyway, tend to be a little bit artificial. It's a little bit like, not to sound too mysterious or philosophical, is an electron a particle or a wave? Because what it depends on the point of view, we'll find out drift and diffusion are both occurring in current transport mechanisms, and this is mostly about drift and this is mostly about diffusion. But still, we normally take these as separate noise sources because in calculations it's a lot easier than getting philosophical. So it's fundamental, it is independent, this is a shot noise, independent of temperature, frequency or technology. Johnson noise I call basic. It's not quite so fundamental because it depends on the resistance value, and you can change that, and temperature, of course. Then there are other sources of noise which are less easy to quantify, and these are due to defects in the material, and they lead to excess noise. There are all kinds of technological factors. We used to be told by something called popcorn noise. And 1.F is still very poorly understood, believe it or not. But there are all kinds of, again, philosophical things that could be said about 1.F. Basically, in, say, an easy example to give is in an MOS channel with a gate above it. some electrons are going to have enough free will and energy to hop through the gate oxide and get stuck there. And then a little bit later decide, well, I got a bit of energy to spare, I'm going to go back into the channel. And these are called trapping sites, of course, and the frequency with which they occur, you can imagine, is moderately low. So there's a corner, roughly at about 100 kilohertz, of course it depends again on technology, beyond which or below which one part noise becomes problematical. It's not even quite 1 upon f, it's 1 upon f to something like alpha. Then of course, there are all kinds of ways of making a circuit noisy by what I call indiscretion. Just think hard enough about where the noises are coming from and dealing with them. One of the things that you may have found yourself in design is you may have designed something that needs a bias cell. Maybe you've been using ideal current sources for a while to get things going, ideal voltage sources. Now it's time to get close to tape out, so well, we better have a bias cell. And you may use something vaguely called a band gap or a p-tap cell, it doesn't matter. But if you're too hasty about that, and you don't spend as much attention on that bias cell as on everything else, you may be in for a shock, because transistors don't know what they're supposed to do. They're mischievous little devils, you know. For example, if you design a cell phone receiver and you stick on a headphone driver, that's what we've got to drive that little headphone, well, that's audio. Well, then when you start measuring the circuit, you find you have a 10 gigahertz oscillator. And transistors are obeying the laws of physics. They're exactly what they're supposed to do. They're supposed to oscillate because there's bond wire inductance and they're very fast transistors and so on. So, in the same way, when lost my train of thought for a moment. When you're designing a little bias cell, you have to treat it as if it thought it was an oscillator or something very close to. And so look at noise versus frequency. It's something you can do with any SPICE-like simulator. Look at noise versus frequency, and it's not uncommon to find some very sharp noise resonances where the noise is 10 or even more times the noise at, say, the mid-band. And the first thing you do when that happens is you drop everything else you're doing and you attend to that. I have a little philosophical point to make here, and we'll never get through all this, but that's okay. I have this notion of a circuit having a certain personality, and that when you are performing experiments on your circuit to determine its robustness, which is a very important part of design. You know, we talk about PVT, process voltage and temperature, voltage in this case being supply voltage, but every circuit exhibits a certain character, a certain personality of its own. And so in order to get it to tell the truth, you should, if you don't, you really should perform lots of sweeps of parameters. And of course the most obvious one is temperature. It's easy to do, but you can sweep many other things. And as you sweep them, I suggest you don't sweep these parameters over what you think are modest and likely ranges. Because, for example, with temperature, I talk to students about this before. I say, you know, what temperature range do you use? Oh, minus 40 to plus 90? Well, why that? Well, that's what the customer needs. Well, that's okay, but supposing in that particular instance you swept from minus 100 to plus 300 degrees Celsius. Now, if you're smart, and I'm sure all of you are, you'll say, yeah, the models are not going to hold up. Well, that's not quite true. Most of the models do hold up pretty well as far as noise generation goes. Certainly something as primitive as a resistor is going to behave just like that. Now, if in your circuit you see something a little bit funny at, let's say it's supposed to work up to 90, and at 100 degrees Celsius you see something funny going on, a little click in the response or a spike or something, you don't ignore it. You don't say, well, it's only going to work up to 90 degrees C. That's a little cry from the heart. The circuit is saying, I don't feel too well, and you attend to it right away. I mean, you must do that. I'm quite serious about this, because if you ignore little things like that, you'll have some nasty shocks when the product comes back from fab. So sweep generously over huge ranges. If you can, embed in your parameterization of your models the ability to sweep device parameters all over the place too. Here's another example of how you can gain insights without accuracy. I introduced a parameter, it's a pretty obvious one, but it modulates the parameter BF, which is in a bipolar model, that's the factor that most determines the DC beta. And I can sweep that from 1/10 normal, well, I sweep it over a lot, but I routinely actually sweep 1/3 nominal to, say, 1,000 times normal. And you may say that's ridiculous, beta doesn't vary that much. And I say I don't care. Because what I'm looking at is some parameter, let's say it's a voltage reference, getting away from noise a little bit. And I look at the output of this reference, and I sweep beta f from 1/3 nominal to 1,000 times nominal. Nothing should vary. If it's a robust design, of course it will vary a little, but what you can often do is you'll see, you want to optimize the situation so that if there is a hump in the variation, a small hump, you place that at the operating point. In this case, beta f equals 1. Well, I'm sorry, the multiplying factor is equal to 1 for beta f. So I think you can see what I'm saying. Sweep everything generously and really make the circuit get on its knees and confess to its sins. Because if you don't, it'll get away with murder. Okay, well, anyway, those are indiscretions in design. They apply to noise as much as anything else. Now, so, slide detail of shot noise we consider later. We'll get a long time getting there, but we will get there in the end. But it is, as you can imagine, caused by the so-called granular nature of current. I say that because the Honorable Carver Mead is insistent there are no such things as electrons, and it's all waves. So talking about granularity of current maybe is against the spirit of his view of the world, and it is a very profound view, I have to say that. But I still think of electrons as little billiard balls and holes as missing spaces in the atoms where they came from. Thermal noise is a little different. It's not a granularity thing now, it's a matter of a distribution of energies, because every element exhibits a certain thermal energy which is simply related to its temperature times Boltzmann's constant. Your brain, working at 300 degrees Kelvin, or 310 degrees Kelvin to be more precise, has a thermal energy proportional to 310 degrees Kelvin, whatever that is, I can't remember. So you have Johnson noise too, but your neural networks are highly redundant, so you don't notice too much. I should tell you one other thing. I'll be here all day, but in going from the retina to the optic nerve, there's a reduction of 10 to 1 in the amount of, quote, data, or the number of nerve fibers to the number of pixels. And the conversion is done in a film of logic, neural logic, that is in fact in front of the photoreceptors. So your light goes through the logic layer before it actually gets to the rods and cones. But there's this reduction of 10 to 1 down the optic nerve. Then you get into a piece of the brain called the lateral genicular module, or
nucleus.
What's that name of that?
Nucleus. Lateral geniculate nucleus.
Nucleus, yes. Where it suddenly expands into billions of parallel channels. And something's going on here that is taking 1 million nerve fibers and doing processing in a very, very parallel way. So you see the noise of individual neurons, which is quite clearly present, is being diminished by the use of many channels. It's an amazing piece of engineering. And I like to believe, and this is really off the subject, that creative thinking is a result of neural noise. That spark of insight is not deterministic. And of course, how you capture that and guide it into a productive channel of thought is deterministic. But the insight is magical, and I think it's just, no, dreams are the same. Dreams, 310 degrees Kelvin worth of dreams. And then we have these many excess things like grain boundaries in resistive materials, in gases where the conduction is by plasmas, the breakdown behavior of p-n junctions, carrier trapping in surface defects, tunneling, and trapping oxide. So these are all called excess, and they're generally said to be 1 upon f. But as I said before, it's more like 1 upon f to signal or some factor. But it's not uncommon for that factor to be as high as 4. But still, we call all of these kinds of excess noise phenomena at low frequencies at 1 upon f. It's just easy to say. That's just an example of an actual circuit. It's not very interesting, but it just shows a corner. In this case, it's at a megahertz, but it's always in that region. I shouldn't say always, but it's roughly in that region. Now, here's another little example, which is a bit out of, it's a bit of an anachronism because we tend not to do this anymore. But here's a transistor that's being used as if it were a voltage reference. The emitter junction is being reverse biased. This is an NPN junction, so that's an emitter. It's being reverse biased, and the base and collector are tied together and just grounded. And This simply shows the typical changes we reference over temperature, and then we compensate that using some other way. But one of the big problems with those references, we used to make them that way, is that we don't need to worry about that. Let me go to the next slide. Okay. And more. Okay. So the breakdown is occurring all around the perimeter of this emitter. And as you can imagine, it doesn't look quite as perfect as that in real life. And it's ragged, and there are small variations in doping densities and the sort of fractal nature of the edge of the emitter. So what's happening is that the breakdown is trying to occur at the lowest voltage, because I think that's pretty obvious. It'll drop down to the lowest voltage. And that will mean that there'll be these little domains that pop up and go away. Now, this earlier slide, I should have mentioned, it was that in a typical breakdown above 5 volts, the older emitters just break down about 8 volts, the temperature coefficient of the breakdown voltage is positive. So when the domain occurs, it heats up that little region there, and the breakdown voltage goes up. So now the breakdown pops to somewhere else where it's more favorable. And so you end up with a peculiar kind of noise. So here's our emitter breaking down over the map. And we end up with a sawtooth of noise, because you can see the voltage is rising as the local temperature rises at one of these points, and then suddenly another point takes over and it drops down back to the low voltage again. So, do you know how that's overcome today? I don't know if this is something that's included in your curriculum. It's a little bit out of date, as I say. Except in high-performance converter products, we tend not to use breakdowns as references. But I had the idea many years ago, I can't remember the years, between 70 and 72, of burying the junction so that it was below the surface, because much of this is due to surface effects where the etching is not quite perfect, and by pushing the junction below the surface, we can end up with a breakdown that doesn't so much from these random variations. That is, a buried scenery is very much quieter than a surface of this sort. But you probably will encounter that in the kind of circuits you design. You're probably using a band gap reference in many cases. Noise in the band gaps is something that we may have time to talk about. I doubt it today, but we'll see. So, okay. So now this is another kind of noise. This is called popcorn noise. And it used to be a big problem at one time in NPN transistors. And it's, again, one of these trapping phenomena. But what we see is a base that is mostly Gaussian. That's the white noise component. And then these energy levels that are discrete and ratioed in a very predictable way. And those are due to the trapping phenomena. And it would lead to, I don't think I have a picture of the waveform, but a waveform where you have noise and it'll step to another level and step down to a level. And there are only about a couple of levels where it jumps between, but it'll occasionally jump to a higher energy state. And that's pretty much gone, I think. But if you hear about popcorn noise, that's sort of the nature of it. Pseudo noise is a reference really to the way that circuit elements or circuit modules may interact. A simple example, you have a little PLL that's supposed to be very, very low in its phase noise because of the modulation requirements, and it's put close to, say, a DC to DC converter on the chip, which is running at some quite different frequency. And that'll put little jaggies into power lines and ground lines and so on, and they may cause the PLL to hiccup occasionally. It looks like noise, in fact, because it hiccups quite frequently on a human time scale, it just looks like noise. But it's not truly noise, it's operating in a non-synchronous fashion. Then, many circuits, believe it or not, can actually exhibit what we would call formal Kähler behavior. That is, it's following a trajectory which is really deterministic, but it doesn't look like it. So anyway, I think that's enough said about some of these basic sources. One thing I just wanted to point out here is if you want to generate a noise source in time in simulation, just use a summation of a whole bunch of sine waves. I mean, I said earlier that, white noise by definition, if you look at the FFT, it's just flat. All the frequencies are there. Of course, they're not discrete components. But even a few discrete frequencies, let me see. Yeah, oh yeah. Let me first mention, there's another kind of noise you have to worry about, that's modulation noise. When a circuit is analyzed in SPICE, it's too easy, maybe, to stick with AC analyses. And you miss the fact that when you change the working point, as an actual waveform comes along and does its thing, the noise is going to vary. That's one of the places where this TNT thing is so useful as well, because you can look at the output of an amplifier or something, and you can actually see how the noise varies versus time. And it's a useful insight-generating mechanism. It's not so much to do with design as gaining these insights. But modulation noise is a big deal. It's particularly troublesome with VGAs, variable gain amplifiers, because almost inevitably, although actually not quite so, you need to, you make reference to the nonlinearity of devices. And as those devices move through their nonlinear ranges, their noise contribution varies. I'll show you a big example of that, a good example a bit later, if we ever get there. So here's the sort of thing I'm showing. This is using, okay, I'm sorry we've lost the title, but this is the noise versus time using TNT. And this is the output of some amplifier that's supposed to be perfectly sinusoidal. And what you can see, you can just about see it here, the noise is varying depending upon the amplitude of the signal. It's easy to see it on this picture, where all I've done is taken the output and added that noise to it, that noise vector to it. And we can see that, as the sinusoid pushes towards some input limit, 400 millivolts, I think it is here, so the modulation noise increases. And again, this is a very deterministic thing. It's very easy to document and calculate and so on, but we're not going to do that today. If you want to talk about it, I'm glad to. So yeah, this is a useful thing to know, that simply adding together a bunch of sinusoids generated by the appropriate function in SPICE, you can generate something that's pretty close to Gaussian. So it's interesting because, first of all, these are the sources, and each of them is a sine. So the basic one is sine 0, that means 0 offset. V sine is its amplitude, F sine is some frequency. But then we use some randomizing parameters, so these phases are not, after the initial startup, these phases become randomized. The nice thing about it is that the relationship between the crest factor and the RMS value is exactly defined. So very often, you'd like to be sure that you're looking at a circuit operating under a certain crest factor. For example, a lot of modern transmitters in handsets and base stations use modulation, which is pretty much black noise, and the quantification of the ratio of crest factor to peak value, I should say. Peak value to RMS value, that's the crest factor. You'd like to be able to set it to some value. In this case, it's exactly 6, and you can figure it out for yourself later on. But it's a nice little trick. However, when I think about it, as I now am doing, you can't really make much use of this unless you have this TNT thing. So get TNT. Okay. And then I have just a little symbol, which is that noise generator, and pop it in wherever I want. This just shows how that noise looks. With a ratio of F max to F min of 100, you can just see the glance. It looks pretty much like real noise. I'll show you some of those in a moment. But you can see that at the start, the phases are, they're a little bit more related. So you end up with, when you start out with a period where things are not quite randomized. So it takes a few cycles. But there's an actual histogram for 2.5 million samples, showing just visually that it looks very much like a Gaussian distribution, even though it's only 18 generators. What's next? Okay. So this idea of current being granular. Current is the accumulation effect of a multiplicity of current carriers that are crossing a certain boundary. We have to define a boundary, it might just be called a terminal, across which this current flow is occurring. And in semiconductors, it's a combination of hole flow and electron flow. Very often, later, I'll be talking just about electron flow for simplicity, particularly in majority carrier devices, that's the appropriate thing to do. But the interesting thing about this is that we know exactly what the unit charge carried by a hole is, or electron, I should say, electron hole, well known. Some of these numbers you should commit to memory. If you haven't, I mean, I really suggest you work hard at it because they come up time and time again. So here's a little example. 6.24 billion electrons per second is 1 amp. But 1 picoamp, in many of the circuits we work on, involve currents of that size, is only 62 electrons per microsecond. But this is something I find rather curious. My point's gone away. If you take the silver, are you familiar with I sub S in a bipolar transistor, the silver saturation current? It's a sort of a mythological thing, but it comes out of very firm foundations. Here's the thing to remember. Most of the early work done on semiconductor devices was based on an analogy to behavior of ideal gases. And so many of the equations of diffusion and things of that sort are based on gas equations. And we tend to forget, as time goes by, that they had a statistical foundation, but we call them, we treat them as if they're scalar numbers instead of time vectors. But if we take a typical transistor, and I forget what I said, at room temperature, its I sub S will be about 10 to the minus 18th of an amp. But at minus 50 degrees C, that'll be 10 to the minus 23rd of an amp, because I sub S is a very steep function of temperature. And that amounts to 1 electron every 4.4 hours. So it's kind of a joke, you say, well, what's the transistor doing between times? But of course, we must understand that this is a drift we're talking about here. There's a lot of fluctuation. That's the noise current, as a matter of fact. We'll get to that. Do I keep saying that? I think I do. So it's granular, and we have therefore to treat it as a statistical quantity, I think we've already covered well enough the idea of an RMS value and a crest factor value. The so-called DC current, I showed it I sub t, but it would be mean I sub t that we're usually interested in, is the summation of all these little units of charge. What am I trying to say? Oh yeah. If we treat it just for the moment, trying to get clever as a wave function in current with, I'll just say, an effective width of Tw and a peak value of that, then the integral of that little lump let's see, that's a lump of charge. That integral is, of course, a current. So each of those occurrences of an electron across some boundary causes a small fluctuation. So here's just a little suggestion here of how we might view math. It's clearly only made up. But I'm giving an electron a certain impulse width here. It's very short. It's about, this is 1 picosecond per division, so it's about 1 picosecond wide pulse of current. And I'm imagining that this is an electron which is like a little billiard ball, which somehow is carrying this bag of charge, and it presents it at the gate, so to speak, as it goes across the boundary. So there it goes, one little lump of current. No, one little lump of charge. So it's a summation of those things that it's going to make a current. But we ask the question, well, what's the average value? Well, of course, that depends on how long you measure the observation. If you measure it over a brief interval, it seems to have one average value. As you extend the averaging time, the average value appears to change. So this is just the beginning of a hint that when we measure total noise power, bandwidth is going to be very much involved, which of course is more or less just the inverse of time. So a succession of electrons follows a Poisson sequence, and there's some nice properties about Poisson sequences that we can invoke to determine the actual magnitude of the shot noise. But this is just a picture of how these electrons sum up, and after summing a lot more, we'll get something like that, and eventually, we'll see no evidence of such big deviations. It's an aspect of a Poisson process that its mean and variance are the same, which is very nice. So it turns out that the current of mean value I has a standard deviation of just root 2q IB. And B again is this thing called the observation bandwidth. Ideally that would be a brick wall filter between really two frequencies, brick wall at the low end and the high end, but usually the low end is reckoned to be DC. Interesting thing about 1 upon f, by the way, before I forget it, you may have noticed that 1 upon f is increasing in amplitude as the inverse of frequency. So what happens at 1 hertz or one cycle per day, doesn't it get to be infinite? Of course, it doesn't, because, you know, in the integration, the effect of those noise components gets diminishingly smaller. If you measure 1 upon f over, say, a 1 second interval, that is, your measurement bandwidth for the 1 upon f determination is 1 hertz, 1 hertz wide filter. And then you measure the 1 upon f over 1 day. It'll be imperceptibly larger. So, and of course, circuits switch off and on, so, you know, the idea of going back to DC is a bit silly. But anyway, the point is that the observation bandwidth is reckoned to be this brick wall filter over which we do the averaging. And it's easier to imagine an average when it goes down to 0, but it doesn't have to. And now this is a very reliable relationship. Bear in mind, as in case anyone should be unsure about this, when we use a current source in simulation, it is reckoned to be ideal. And all of the noise is reckoned to be generated by the devices that it drives. Of course, the same is true of voltage. So we can write the bandwidth in this particular way of looking at things, certainly if the lower frequency is DC, as simply 1 upon the interval of observation. So we can write it in that form, and you notice that the dimension of Q upon T is a current. So the square root of that quantity comes out being back into the current mode. Okay. Now, here's a thought. You may ask, well, what's the dynamic range of a current? Now, again, an ideal current would have infinite dynamic range if it doesn't have noise. But to the extent that it's going to operate on a junction device, shock noise becomes one of the most important noise generators. You ask, does a current really imply a certain dynamic range? In other words, can we get 110 dBs of dynamic range at a 1 picoamp current in a junction based junction transistor circuit? And it's very easy to make the calculation, but the signal noise ratio is simply, if you like, the mean current, which tells you sort of the amount of variation that the output current of some element can generate, divided by the noise associated with that in, at least one junction device. And that comes out to this. So, in other words, there is a certain dynamic range associated with any current when used in a junction circuit device, a junction device circuit. And so here's a little example. What is the shock noise spectral density for a junction device at a milliamp? Well, the shock noise spectral density is 17.9 picoamps per hertz. And then we say, well, supposing we have a bandwidth of 300 kilohertz, and now we raise that current to 10 milliamps, what's the signal noise ratio? And it's only 80 dBs. So what this says in so many words, and I think I may have a little side note here, that's something else, but it says something that should be obvious intuitively, and that is that because a circuit has a certain thermal energy kT, no matter what you do, if you lower the operating current, you are worsening the competition between signal and noise. The noise isn't going to get any better just because the current's smaller, quite the converse, in fact, in many cases. Now, the shock noise gets better by square root of current, but the voltage noise generated in the junction, as we'll see, gets larger. I just happen to mention here in passing that a 50 ohm resistor has roughly the same noise spectral density as the Johnson noise. If that much shock noise were applied to a 50 ohm resistor in say a load of some sort, it turns out being almost exactly equal to the noise of the resistor itself. And I say the precise crossover occurs at 51.93 ohms. Just a little facet, just a little factoid. Okay. Are we getting there? So we have to ask, well, how does this shock noise manifest? I mean, it's something to do with electrons appearing at a cross section, a barrier of some sort. Well, again, it doesn't take much imagination to realize that the barrier that we're going to be talking about here is the potential barrier associated with a p-n junction. Shock noise is not going to manifest itself quite so evidently, again, these two are, they overlap so much I have to be careful what I say, but in a field effect device, where all the conductors by drift in a majority, carrier as a predominant carrier current, it's essentially resistor noise. There's no shock noise associated with that. So effect does not suffer from shock noise in the way that a junction device does, where a potential barrier is a place where we can actually sort of count and watch the passage of electrons or carriers. Let me see if I can make that clearer. I'm digging myself into a deep grave here, but we'll see. So now it's important to understand this is a reverse bias junction. This is not the emitter junction bipolar transistor. It might be, you say, a photodiode or a collect junction transistor. But we can reckon that we have the light and gets into trouble here, but a reference plane across which we're counting the appearance of these other things called electrons up here, which, with due respect to carbon mean, are billiard balls, lots of little billiard balls. And they are attracted by the field of the collector, and of course, once they're on the other side of that boundary, they're not going to get back up. At least the probability of them getting back up is extremely tiny. So I show here if the reverse bias on that junction is 480 millivolts, the probability of an electron having enough energy to get back is about 1 in 10 million, 300 Kelvin. So they go over and they become the current that we use. But you can see the granularity is sort of demonstrated quite well by this thought of a bundle of electrons, which this is the base charge. Well, I haven't said there's a transistor yet, so I better not say that. Okay, we'll get to transistors. Oh! Gotcha. Now, one of the important things to understand, and some of these things I apologize for being a little bit philosophical about it, but we talk about the collector shock noise, and it is indeed proportional to the collector, or rather, it is related to the collector current by root 2 ICQB. It is the collector current that's in the driver seat. However, you still have to ask, where does the noise arise? Because if all those electrons had the same energy, then they would fall across that barrier in a very predictable way, almost in a sort of periodic fashion. There may still be some ripple, but it wouldn't have a high degree of variance in a stochastic sense. In fact, these electrons have different energies because they made it across the emitter boundary due to the injection process, which isn't included in this picture, it will be in a later picture. And there are, again, the ideal gas analog for understanding the behavior of a semiconductor. It lacks in a number of ways because we forget that it's all statistical and we think of the band gap as being an absolute voltage. In fact, the band gap energy has a distribution. It comes out of the density of states. There's an energy distribution of those carriers, and some of them will make it across the boundary and some won't, but to the degree that the top level energy electrons, the highest energy electrons, make it into there, they carry that energy with them across the base, and they appear at random times in the collector, but it's actually emitter. The noise of a bipolar transistor occurs at the emitter, but it's referred to the collector because when all is said and done, you go through all the math, it's proportional, or it's dependent on the collector current, not the emitter current. But part of the reason for that is there's a lot of the base current is a kind of a defect of the transistor. It's just it's said to be due to recombination, but in a modern transistor, it's mostly due to surface effects. Okay, I think I'm going to jump over some of these because, well, yeah, I think, forgive me, but we'll leave photodiodes out of this for now. Okay, let's quickly move on to resistor noise, and we asked why are resistors noisy? And as I said earlier, the energy available at any system at a certain temperature is just kT. So associated with that resistor is some energy, and it will lead to a certain noise voltage, which can actually be measured. I mean, it's not a myth. It really is. There is a voltage there. Now, of course, its mean value is 0, and there's no energy transfer associated with looking at the voltage across that resistor, but still there is a fluctuation. But let's see if we can get to it quickly. There's all kinds of ways of getting to the answer here, but power is expressed as energy per unit time. So if kT is the energy of the system, and T is the observation bandwidth, or time I should say, or KTB is the B is the bandwidth, then we can take a step which will let us absorb some power from that resistor and calculate what En is. And I'll show you what I mean. Suppose we put another resistor across the first resistor of the same value. Then the presence of that load resistor would make the noise of the resistor on the left just En upon 2. It's just a loading effect. Now, that's not exactly what En would be. We'll get to that in a second, but you can see what I'm saying. That the first thing you could say is that, well, for the left-hand resistor, we'll get En upon 2. Just because we've loaded R, I equal resistor. So, the point is here that the resistor on the right is also the same thing. It's contributing En upon 2. So, the amount of power that is being transferred back and forth across, say, the top connection between these two is expressed at the bottom. It's just En upon 2 squared. That's the En upon 2 squared. This is the B squared over R is what I'm trying to say. So this is the B. I'm pointing, I'm sorry. This is the B, and we square it, and then the power in each resistor is En over 2 squared over R. But this has to be equal to KTB, because that's all the energy we've got to talk about here. And so we just can do that identity and come out with the N squared is 4 KTBR. I'm not sure if that was clear, but it seems to me to be a simpler way of understanding resistor noise than some of the other analyses I've seen. So this is one of those numbers that I implore you to remember. The noise of an ideal 1 ohm resistor at 300 Kelvin, which is of course a pretty common kind of place to do analysis and so on, is 0.129 nanovolts per root hertz. And the noise of any value resistor is simply going to be multiplied out by root R. So this is a 1 ohm. So here's an example. But so this one example here, 100 ohms is 129 picovolts times root of R. Well, for 100 ohms, root of R is 10, and the noise of 100 ohm resistor is 1.29 nanovolts per root hertz. And of course, everything follows. It's just very simple. But it's easier to remember this than calculate that every time. And it gives you a sense of what you should expect. And if you are designing a circuit which has a 1K resistor in series with its input, you've got to be sure that you don't care about at least that extra 4 nanovolts per root hertz of noise. Now, sometimes the question comes up, what is KT upon Q? KT upon C. On capacitors noisy. One of the things, though, it's worth thinking about a little bit, is that since the charge on an electron is a discrete quantity, then we can only change the voltage by discrete jumps, because we can only add or subtract 1 electron at a time. So, if we ask how many electrons constitute a millivolt stored in 1 capacitor, and the answer is 6,250 by 12 bits worth. So that tells you something about the granularity of charge. It's not the granularity of charge across the barrier now, but it's the discrete jumps in voltage. But this is not noise. So I show if we apply a certain number of electrons between 1 and 10,000 to a 1 capacitor, then this is the percentage voltage change which will occur for each additional electron. Of course, at the 1 electron point, it'll be 100%. By the time you get to 1,000 electrons, it'll be down to 0.1%. The voltage on the capacitor is rising as we're adding electrons, but these are actually discrete jumps. And nowadays, we use a lot of very tiny capacitors. It's not uncommon to find capacitors around the femtofarad range, and you can really consider single electrons as being involved in some transactions. But again, that's not noise, that's a communication limit. KT upon C noise isn't the result of charge granularity. A capacitor is not dissipated. There's no loss associated with an ideal capacitor. And in spite of the fact that it's a common metric, because it says to us very plainly that if you want a circuit involving lots of, say, switch capacitors to be low noise, then you have to use large capacitors. There's no way around it. That's the nature of noise. It doesn't give you much room for messing around. So we're going to ask, so why does that happen? Where's it really coming from? Well, let's just take a simple RC circuit. It has its noise associated with KT. Capacitor over here is a non-dissipated element, so there's no consequence of you sort of, again, you can imagine this intuitively. Imagine two plates separated by a vacuum or by air. You can see, particularly if you have a vacuum capacitor, that's the best example. Vacuum capacitors are used in transmitters, for example, because otherwise they might arc at high voltages. But if you imagine a vacuum capacitor, you can see there's no granular motion to talk about. There's nothing going on between the two plates. So anyway, in this simple example, we have a low-pass filter, and if we calculate the squared noise at the output, it comes out to KT upon C, just because we have this as a transfer function of the filter. But now R is gone, and if you really don't believe that simple little demonstration, here's somewhere here. Just as a series of sims, it's not very interesting, but I just changed the resistor from R to 100R or 100th of R, and again my picture's unfortunately a little bit cut off here, but they all end up at KT upon C of 4.1 per hour was reversed. So it seems like the asymptote in terms of the voltage noise spectral density is related directly to the capacitor, but it's really just a consequence of that integration over time. It probably doesn't make a lot of sense, but anyway. So, as I mentioned earlier, the distinction between shock noise and thermal noise is a little bit blurred, because both are due to random motion of some sort. But one of them is due to carriers which are moving under drift conditions. And in the other case, the variance is due to diffusion. I notice here that other things like inductors and high-Q crystals and MEMS resonators are essentially noise-free in principle, but in practice they also have a little bit of a loss due to various effects, such as the series resistance of a capacitor or an inductor, and the frictional losses of a resonator. This is actually a picture of a flock of geese taken over O'Hare Airport last Saturday. And it illustrates drift and diffusion pretty well, I think, because you can see there's a general forward motion of these carriers, not carrier pigeons, maybe I should find some carrier pigeons. And that is the what we call the granularity aspect, because obviously even if they were coming along from a nice formation like this, there'd still be a distribution in time. That's the Poisson sequence we see here. But there's also this diffusion. There's some difference in energy of these geese that cause them to be now and again at the front and now and again behind the front of the flock. So that's the diffusion component. But again, a flock of geese is a flock of geese, and whether we talk about their velocity over Virginia in miles per hour, or look at the variance in the front end of the flock, that's up to us. It's a matter of viewpoint. Now that was supposed to be the midpoint of the 1.5 hour thing, and in fact it is about 1.5 hours. Whether we've got time to go on to the whole story here or not, I don't know. I don't quite know what's the best thing to include. We'll just keep cracking on for a while. Bear in mind that you can have these slides and you can do what you want with them. So it's useful to remember that particularly in bipolar design, bipolar circuit design, there are important temperature shapes that matter a lot. And the three most obvious ones perhaps are proportional to absolute temperature, complementary to absolute temperature, which is the basic shape of VBE as a function of temperature, and Z-tab, which means simply stable. But then there are other forms which can be super P-tab, very, very ultra zero, that means to say having a very low temperature coefficient. and so on. So these shapes matter because the performance of the circuit will depend a lot on our right choice of T-shapes. So I put it in passing because sometimes when we're talking about circuits in which the currents are not constant with temperature, but PTAP, being the natural language of a bipolar circuit. And again, KT upon Q occurs frequently. I think I might adopt the convention of calling it V sub KT rather than VT because, that could be a threshold voltage of an MOS. And VKT has a well-defined value of 25.85 millivolts and 300 Kelvin. Another way of looking at it is as 86 microvolts per Kelvin. It's a very important quantity. So here I talk a bit about I already talked about simple terminations being a bad deal. Can you see why? I mean, apart from the math there is, but can you see fundamentally why that's a bad thing to do? Just looking at it as an energy system, a power system. What does a resistor do when a voltage is applied to it or a current passes through to it?
Specific power.
It gets warm. Yeah. Where does the warmth come from? The heat is, of course, the power dissipating that resistor. So, remembering that what's coming into the antenna is an itsy-bitsy bit of power. We don't want to waste power by burning it in a resistor and warming up the lab. That's all that does. It just consumes power rather than sending it forward into the signal processing part. So that's the termination. It's not a good idea. Okay, so I show an example here of matching. Of course, it's a very old idea in electrical engineering. Here I show a generator in Interlaken, since this is given in Lausanne. And over here, not far from Interlaken, is Brienz, a little woodworking town. And there's a generator over here that's pushing out 2.5 megawatts. And if this town does not look like 50 ohms, if the generator is 50 ohms with 16K volt level, then we won't be transferring as much power into the town as we could. Obviously, if it goes higher, less power is transmitted. If it goes lower, less power is transmitted. That's a well-known matching theory, and it applies universally through circuit design. But what can we do in practice about it? One way of thinking about it is we want to use both the voltage and the current available from the power signal. You see, in that first example where we just put a termination resistor on the source, we ended up only listening to the voltage. We had like a low noise voltage amplifier. You could use, let's say, a current feedback amplifier or some other topology in which you only use the current through the 50 ohm resistor, terminating into something like a sort of virtual rack of some sort. But we want to use both. And the trick is to arrange matters so that, that happens, and there are lots of ways of doing that. So this is one approach, which is more of a circuit level approach than a device level approach. I'm assuming here that we have some amplifier whose gain will be defined in a moment. In fact, I guess it is A. Voltage gain minus A, the feedback amplifier, and a feedback resistor. Now, this is still called the termination resistor, but it won't be the value of Rg because the gain is getting into the act. You can see that the higher the gain of this amplifier, the higher this resistor has to be for the current that's absorbed in it to be equal to the current available from the source. There's no current at the input of this amplifier. So let me just go through the math a little bit. It's not all that convoluted. We want the input. I'll say impedance is easy to say, it's really incremental input resistance, but we want the input that needs to be Rg to match the generator. So that current is going to go into the feedback resistor, and because we've performed matching, this is a 2Vg, so we've asserted we're going to make that happen. We want Vg upon Rg as the current through this resistor. So that's another direction through which we can calculate the output voltage. And the voltage appearing across this resistor is simply 1 plus A times Vg, because this is minus A at the output, this is 1 at the input, and 1 Vg that is, and so we've got two routes now for calculating the voltage. We've got the current through this resistor, and we've got the amplifier, the resistor. and we simply equate those two. So the current in the resistor, that's the slash there, hard to see, it's a slash. VG over RG must be equal to 1 plus AVG times RG. That over RG, excuse me, and that's really all there is to the math. It's not so hard, except you can't see the slashes. So the required value of RT is easily calculated. It's just simply 1 plus A times RG. So the higher, as I read, the higher the gain, the higher this feedback resistance is going to be. But what's important is what happens to the noise. Let's see if we can get to that step. What's going on here? Okay. So the first thing I do is I say, let's consider the noise of this resistor. It is easily asserted because we know the value of the resistor, and we put it in here as a noise generator. And equate it to root KT or root 4 KTB. Now, it's been a while since I showed these, so give me a bit slow. Yeah, what I'm saying now, hello, come back. It's supposed to be at the top of the screen. What I'm saying here is that this noise voltage is divided down by 1 plus A, because, again, the voltage magnitude between here and here, due to the minus A of the gain stage, is 1 plus A. And we divide it up into a little bit at the input, which is 1 plus 8 of the noise of this resistor, and a bit at the output, which is minus A times bigger, or A times bigger in magnitude. So we can look at the noises going through places, and that allows us to move the noise generator to a different spot, like that. It may be better if you study these in your leisure or in your bathtub or wherever you do your studies. It'll be too much of an impediment to be super precise about all this. Maybe all I can do really is give you a flavor of what's going on. The point is this. Let's get to the bottom line. The point is this, that the noise factor, remember the factor was the ratio of the signal noise ratio at the input divided by the signal noise ratio at the output. And the noise, corresponding noise figure in power terms is that. That tells you very clearly that as A is asymptotic to infinity, not that an op-amp does that for you, because remember, that's not an op-amp that I showed. It's an amplifier of fixed gain A. You can make it with an op-amp, but op-amps, by the way, don't go too much. There are lots of ways of making good amplifiers. And there are some fundamental flaws that we talk about on another day. But so as A gets very big, then so the noise figure and the noise factor both get very small. And this is actually a very workable principle. It's not one of those things that power back. This is really used very often. So let's see if we can do an example here. The basic building block of almost any amplifier starts out with some sort of GM. Either a grounded source transistor or a differential bipolar pair or whatever it might be. It's transconductance, so its input parameter is a voltage, the importance of the voltage, and it generates an output current, which is GM times VM. And I'm not sure if I got the direction of my arrow right here, but it depends on which you call the positive negative terminal, I guess. But the way the terminals are shown, I suppose the current will be going the other way. We'll get there, I hope. So now, let's take that GM and put it. What we're going to try to do is take a signal source of the same impedance, ZL, and arrange for this to have to look like ZL at the input. Let's say 50 ohms, because that's common impedance. But of course, the GM by itself is only using the voltage of the source. So that's not going to lead to a low noise amplifier. We want to use the current in the source as well. But for the moment, let's replace the complex impedance by a purely resistive load. It makes life easy. And now add that feedback resistance. It's doing the same thing as before, except that the amplifier now is made by the GM working against its load resistance, or actually against the shunt feedback resistor. So let's see what I'm trying to say here. Yeah. So for a certain V in here, there's a certain I out from the GM, that's just because of this convention, and that is divided partly to the load resistor and partly to the feedback resistor. However, the current in the feedback resistor, if we now specify an input current here, remember this is a high, so the IN is the current coming from the source, it flows in RF, and what's available here flows in both RF and R0. It's split between them. So the gain of the amplifier is not quite as clear as it might be before, but let me actually rather quickly jump to a conclusion, because it's a pretty amazing conclusion. Forgive me for being quick. Here it is. It's so easy to get this right. If you have a GM device, let's just say it's grounded source transistor, I don't really care, and you wish to match a source resistance with R0, which, by the way, it may not be an antenna. There's all kinds of signal sources. For example, in ultrasound, we're faced with the equivalent source resistance of a piezoelectric crystal array, which in itself is pretty complex. But generally speaking, people like to assume it has a nice simple number for an impedance. It's a bit of a mistake. They do that anyway. And so you want to match this, which may be 200 ohms, to an amplifier. So it's not just RF in the ordinary or wireless sense. So you want this to match, and you wish to obtain a certain gain. So you decide what the overall voltage gain of this amplifier needs to be, and then you bias the GM so as to set it to this value. So you deliberately choose a bias current here so that the GN is A plus 1 over R0. And then, having done that, you set the value of the feedback resistor to A plus 1 times R0. I mean, there's a lot of symmetry there, and that's why I like it. It's so simple, you may forget where the slash goes, but it shouldn't be too hard from a dimensional point of view. It shouldn't be too hard. As a matter of fact, there's an interesting philosophical way of getting at the resistance value, which we can talk about maybe some other time. But so it just really what I'm trying to say here is that the management of noise in circuits doesn't have to be complicated. It doesn't have to be surrounded by some very long mathematics which tries to include the whole universe. Clearly, this is a little bit lacking because we haven't yet said anything about the voltage noise at the end of the GM. But at this point, we're asserting, I am asserting, that this configuration by a previous demonstration is the lowest noise configuration, where the matching is done by feedback. And now I'm not talking about noise anymore for a moment, I'm talking about how you design this amplifier for a given gain. So you choose the gain, choose the bias, and choose the feedback resistor, and you're all done, you can go home. Or if you're more, interested, you can keep going and figure out more funny things about circuits like this. So this is just an example of 50 ohm bilateral match. By bilateral, of course, we mean that we want the circuit to look like 50 ohms looking back in here as well, because many times we'll be driving something that doesn't like to have reflections, or that is upset by reflections. For example, a long cable that is improperly terminated at both ends. Now, if it's well terminated at the load end, there should be no reflections, but usually it's not. And so any reflections that come back here should ideally be presented with the same cables. Absorption is maximized, the reflections are minimized. But it could be a filter. Very often a lamp like this would provide a SAW filter. And the SAW filter needs to be driven from and loaded by certain very specific impedances, which the manufacturer tells you. And so bilateral matching is often important. Anyway, so supposing we need a gain of 18 dBs, a gain magnitude of 8. We're just going to go through that silly little sum again, but we'll do it. So that means we have to set the GM to 180 millisiemens. And it means that the feedback resistor has to be set to 450 ohms. And as I say, that's really all there is to it. The low noise aspect we've taken care of by a topologically favorable approach to the amplifier design. Here's an example of how that might turn out with a bipolar transistor. It's a very interesting thing that you can. I wish I could have this screen. We can bias this device here just by a current applied to that top node. Maybe if I use my own cursor, I keep pulling over my trousers. Yeah, so if we apply a current into this node, then that will actually bias that transistor up automatically, because it's now acting like a diode with a resistor in its base, and yet it's an amplifier. So you can really do that. You can make little bipolar amplifiers just exactly like this. And there's the 450 ohms that came out of our previous analysis, where we had to get our 0.18 Siemens or 180 millisiemens. Well, to do that, we need to use a collector current of 4.65 milliamps. And I note it should be PTAT because we want the GM to be constant with temperature. The GM being IC over BKT. So, this shows, and I bet you it doesn't show up very well. For a moment, we'll go into deep darkness here. This is a little simulation in which I'm varying the collector current from a microamp up to 100 amps in an experimental variety. Actually, I should say, in this case, an ideal bipolar transistor. Another thing we should talk about someday is the idea of foundation design, where you start out with a very ideal device, and little by little add reality to it and watch what happens. Because a truly ideal bipolar transistor, no resistances associated with junctions, no capacitances, a very high beta that's almost like a bipolar MOS transistor. It still does most of the things that a real transistor will do. It's quite amazing. At a certain current, we see here, this is the, remember I told you how to calculate the noise referred to the input. Or rather, I should say noise figure, excuse me. The noise figure is 20 times log base 10, the measured noise at the output of the amplifier, divided by the noise due to the R1, which was the source in this case. So you see that at a certain current, it reaches a huge noise figure, which is totally unacceptable. Of course, that corresponds to a point where the gain is 0. Now, that happens because, let me see if I can illuminate that a bit. Blinded by the light. I think you can see that if you just visualize that, close your eyes if you like, and visualize that little amplifier, at the input, you have a certain voltage swing, and when the gain is exactly -1, the value of the voltage across the resistor exactly cancels the input voltage, because they're out of phase. So there's a certain magic curve, not very useful magic, but where the gain goes to 0 because the voltage across the feedback resistor and the input resistance cancel. And that's that point there. You don't operate there. So you pop up a little bit, and this doesn't depend upon the process, doesn't depend upon the polarity of the device, doesn't depend upon a lot of things, but it's very fundamental. Anyway, so you move up the current a little bit, and at a certain point you begin to get into favorable territory. So this is the gain of this amplifier, voltage gain, and supposing we wanted the voltage gain of 20 dBs, well, to get there we need to operate at about 2 milliamps, and by that time the noise figure has gone down to about 1 dB for an ideal transistor. So this is one way of thinking about things, because clearly you're not going to make this thing work down here. You'll have the reason the noise figure is 3 dBs here is simply because eventually, at very, very tiny currents, the feedback resistor gets to be, how does it work? It simply becomes equivalent to a simple termination resistance. I'm trying to remember the mechanism, I shouldn't forget these things, but if you do the sums, I think it's better to do it yourself anyway. I can just sort of push you in the right direction, let you get on with it. But you'll find it just behaves like a termination resistor with a noise figure of 3 dB down here, for however low the current goes. Got to think about that. But anyway, and then this line here simply shows that even though we're varying the current over a huge range, don't forget we're varying the feedback resistor algorithmically in the simulation to be correct. The 50 ohms remains constant over the whole range. So again, it's just a little demonstration of a simple idea that leads to quite a few insights. I think we'll jump over that one. Whew. I want to just talk a little bit about the BJT. How many people here are using bipolar processors? Oh, we've got to change that. A hesitant hand there. Someone who doesn't want to distinguish herself as being a rebel. Well, bipolar is not dead. by a long chalk. Here's one way of sort of, what should we say, demonstrating that you should become BJT savvy. Over the past few years, TSMC, which of course has been recognized as one of the largest foundries, if not the largest chip foundry in the world, has been introducing BiCMOS processes. Turns out that the bipolar part comes from analog devices, so we have a close connection in that regard. And we're now integrating some very fast silicon germanium stuff with 0.18 microns over there, and unfortunately that's going to be a generally available process. So you'll benefit, but from a competitive point of view, we lose it. But we do get 0.18 micron CMOS in exchange. Anyway, why do you think TSMC would go to all the trouble and expense of making BiCMOS processes if bipolar was obsolete, dead, useless, old-fashioned? The fact is it isn't. You know, modern bipolar devices are doing some pretty stunning things. And even though at conferences like the ISSCC, where almost all the papers, it seems, talk about 65 nanometer implementations, it really belies the fact that by far the largest proportion of products out in the market today, I mean analog signal processing products, still use bipolar or BiCMOS processes. I say still use, I mean they use them beneficially. So don't put BJT aside as if it's a no longer important technology. But anyway, a couple of things to say. The old idea of current gain as being the important property of a bipolar transistor is really incorrect. The base current is just a defect you'd rather not have. And in fact, you can make bipolar transistors with DC betas of thousands, but they're not manufacturable. I mean, I don't mean to do it by some kind of tweaking of the process. You can use a tunneling emitter, for example, and get very, very high equivalent betas. And secondly, adopt the view of the BJT as a voltage-controlled current source, just like you would in MOS. So in other words, ignore that pesky base current for the moment, because you know, the gate current of an MOS transistor is not zero. I'm not talking about tunneling. I'm talking about the AC current in the base of an MOS transistor, where wherever you're trying to do things at frequency, that gate presents an impedance that is actually a reflection of the gate resistance coupled with the gate capacitance, a complicated impedance. But it's there nonetheless. I think the BJT is a bit more troublesome in this regard, but focus on its transconductance. And it's that which is remarkable and a very reliable property of all bipolar transistors, meaning those using minority carrier current transport. And then I say frequently, for circuits operating on moderate frequencies well below the FT of the transistor, we can ignore inertial effects at least for quite a while in getting some idea of noise behavior and other aspects of modeling. So the most important stuff is going to be shown here. There's our grounded emitter transistor with some voltage source, in this case, driving the base, and some collector voltage, VCE. We ignore the base current. And we know some pretty fundamental reasoning that the collector current is equal to the saturation current, that mysterious current we talked about before that's so tiny, times exponential VP over VT, or VKT if you like. So that's the beginning of it. But think of I sub S as the scaling current. You see, if you're going from the domain of voltage as the input to current as the output, there must be some scaling parameter. It may be resistance, as in the case of, say, an MOS channel, where we tend to talk about GM. But here, there's a separate scaling factor which is controllable to a large extent by us, because we can choose to make this device as big or as small as we like, and the I sub S is roughly proportional to the area. Not roughly, actually, quite closely proportional. But then there has to be, because it's an exponential property, we cannot take the exponential of the voltage. It has to be scaled, and marvelously it's scaled by KT upon Q, and that's really the whole story. You'd be surprised how close to reality that is. You wouldn't, but it still surprises me. Now we can turn this around and say that for a given collector voltage, the VBE is going to be thus and so. And this again, I mean, it's the same thing, just put it around another way, but these are very dependable ideas. Now I have to add one note of caution. Modern transistors are very, very tiny often. They don't have to be, you can make them whatever size you want. But you often, for inertial reasons, make them small. And if you're working with a technology such as silicon on insulator, many of our complementary bipolar processes are silicon insulated, the thermal resistance of the oxide is very high. It's 100 times higher than silicon. So what happens is you get local heating of the device. And the characterizing parameter is degrees C per watt. And for the smallest transistor in one of our complementary bipolar processes has a thermal resistance of 16,000 degrees C per watt. So think about that. If you just apply a milliwatt of power, you're raising its temperature by 16 degrees Celsius. And in bipolar land, that's a big difference because you may remember that what am I trying to say? The slope, which is, by the way, not writing as a constant, if we take, let's say, minus a millivolt per degree C, that's a 16 millivolt change, and that's roughly a 2-to-1 change in current. So anyway, it's a big deal. And there are ways of dealing with that, some of which work and some of which are not so good. A simple example might be to try to put transistors that have to match in a more complicated circuit, put them in the same pocket if you can. Of course, you can't always do that. So anyway, thermal consequences are very serious. But then getting back to another wonderful thing about a bipolar transistor, excuse me for enthusing, but the GM is just that. It's just the collector current divided by KT upon Q. And again, it doesn't matter how you make these parts. That's the nature of a junction device. Because its roots go deeply back into physical phenomena in a way quite unlike the way we have to deal with channel conduction in an MOS transistor, which is very much empirical affair. So that makes a bipolar transistor a delight to design with, but you can also do some very useful things with that. So what we can do at times, when it's convenient, is to talk about an incremental RE. This, of course, is not a real resistor, which is why I use a pink thing, or lavender resistor. That means that, instead of talking about GM, we can talk about the equivalent RE, and that is often a useful thing to do. But again, it's a very simple, it's the same thing as GM upside down, but it's very simple. Okay, now here's another remarkable property that doesn't come directly out of anything we just said. The BBE of a bipolar transistor falls almost exactly linearly with temperature. And that is often explained by what happens to I sub s, which is a very complicated function of all kinds of things. Actually, the density of states, Ni squared, includes Planck's constant, E, pi, the number 32, the number 3 degrees of freedom, the band gap, temperature, of course, but it's a lovely thing. It goes right down into the roots of physics. And it's out of Ni squared that we get I sub s. And if you go through that route, sure enough, you'll end up realizing that's what happens to BB. But can any of you see intuitively why it does that? Come on, you leaders of the world of tomorrow. Why should it do that? Well, what's another way of thinking about temperature? Yeah, it's an energy. What's another way of thinking about energy?
Boolean electrons, like faster jumping back and forth.
What is an electron volt? It's an energy, isn't it? So energy, voltage, temperature are all linked linearly, proportionally. So what's going on, and I got a little picture here to explain this, but I've never seen it explained this way. It seems to me a useful thing to say, that if this is the BBE of a transistor, then the amount of energy coming from the background temperature is kT, and that gets us a certain amount of conduction, because I sub s, you see, is increasing the temperature. And some of the carriers are being provided generously by temperature. We have to supply the rest. So the rest is this much in this case. This is determined by the environment, and this is determined by the bias. So it's a summation of a pair of things, but you can see quite readily that as temperature increases, this triangle just descends proportionally back. And there's nothing here. This is TZ. This really happens, believe it or not. This is the temperature at which the BBE is 0. And it's pretty high, depending upon the size of the device, but it's it's so important in practice, believe it or not, that in an electrometer logarithmic amplifier that we have several now in the catalog, but we measure currents down to a picoamp. And when a picoamp is applied to the logging transistor, the VBE actually goes negative at high temperatures. It behaves like a depletion device. You've got to actually pull the lever back on the base emitter voltage because you see, it's very simple. The I sub S is so big. I sub S has exceeded now the 1 picoamp you're trying to measure. So VBEs can go negative, and that's not a joke. That's a reality. You don't often come up against it because it only happens at low currents and high temperatures, but it does happen. So as I say, that's the rest that we have to apply. Now, this is just to show or remind you that what we often talk about when we talk about the slope of VBE versus temperature, it's by no means a constant, like 1 millivolt per degree C or 2 or something. Again, if I can just permit me just to veil. So here, this line, these are all VBEs versus temperature. This line is at 1 femtoamp. We don't normally work down there. But 1 picoamp we do work at. You can see that as the current increases, so the slope decreases. And so at moderate currents, like a milliamp, it is pretty close to a millivolt per degree K. Not the 2 millivolt per degree K that's often stated, by the way. And as we go up in current in this imaginary device, by the time we get to 1 amp, we're at a very low slope, and it raises the question, can you operate a junction device at such a high current density that the voltage is constant at the band gap voltage? Well, I didn't mention this, I should have done, but all of these curves converge on the band gap, which for this particular device is about 1.14 volts. The band gap is a little bit less in practice than in theory. Theory said it should be 1.206 because of a number of factors. The doping lowers the band gap energy. You can see why that is, because you're disrupting the lattice, and that's going to make carriers more likely to be available, more vacancies will be generated. And suddenly my mind's gone blank again. Anyway, so the long and the short of it is that at 0 degrees Kelvin, the GM becomes infinite. Remember, GM was IC upon K upon Q. So what it's saying is the GM goes up and up and up as the temperature goes down. And if you could operate a device at this temperature, then you'd have to apply no voltage to get any of these currents. They all come to the same point. Anyway, so the question is, could you make a device such that the slope is so low that it's constant with temperature? Well, you can't, because you can see how big those current densities have to be. But you can easily add a p-tap voltage to any one of these lines, and that's something of the band gap, which is a separate topic. We are just beginning to talk about shock noise in a transistor. Isn't this awful? So, very quickly stated, the emitter junction is forward biased. This is MPN. So we have negative bias on the emitter and positive bias on the collector. Sorry, it's upside down. And we've loaded up the base with a certain base charge, we want to see if we can get some insights as to the noise mechanisms going on here. The charge on the base is that. The transit time is finite across the base region. And so the collector current is the total amount of charge in the base is falling over that waterfall, if you like, the collector junction in the transit time TB. Now, getting back to that little picture of drift and diffusion, I think you can see that in the base here, we have two things going on. We have the quantum nature of these little electrons reaching the boundary and being swept across the field in the collector junction. But we have the energy distribution here caused by slight variations in the band gap voltage of a statistical nature. And it's that little, there's a kind of selection process going on at the emitter where the higher energy electrons that present themselves at that terminal coming out of a majority carrier element like a metal or a resistor generate a distribution of energy in the base. So I say these carriers have different energies. There's a drift field. Modern bipolar transistors almost always have a drift field built in due to, say, the use of germanium doping in a silicon base. But carrier transport is by both drift and diffusion processes. In an older style monolithic transistor, it would be almost totally by diffusion. But there's here a drift field as well. So you can see that the point I'm making is just like our flock of geese, there's a drift aspect to this current and a diffusion. You can begin to see why the intractability of so-called thermal noise and shock noise gets to be a little bit fuzzy. Now, I think I'm not going to go much further because this really begins a long litany about how to calculate noise in all kinds of situations. But I just want to say one or two little things about noise in a bipolar transistor as the talk gets close to midday. This is how the noise source is represented. It's root 2Q IC, if you remember. And it doesn't matter about the sign here doesn't matter. This is a variance. It's just perturbing by that amount, so it's perturbing by the same amount in the collector. It doesn't do anything much associated with the collector resistance. But by the time it encounters this incremental resistance in the emitter, it's going to generate a noise voltage across it by the simple multiplication of the shock noise and the RE. And that comes out as this, which it's useful to remember that at 300 degrees Kelvin calculates to about a half a nanovolt per root hertz. It's not too hard to remember 460. Per root hertz divided by the root of the collector current expressed in milliamps. It's just one of those things that, you should have at your fingertips. You should know what the noise of a 50 ohm resistor, or noise spectral density, I should say, of a 50 ohm resistor is. Because they're so important that you can't afford to refer to textbooks, particularly when they're big and thick, as they sometimes are. Now, I have many slides that go into the detailed analysis of the differential pair, but I'll leave you to look at those at your leisure, if you wish. But just a point to be made is that when two transistors are connected as a differential pair and they share a tail current, then clearly each device is working at half the tail current. And because there are two devices making non-correlated noise, the noise is 3 dBs higher because of that. So there are two reasons why it's 3 dBs higher: the halving of the tail current and the doubling of the sum of the vector sum of the two noise components. So it turns out that for a differential pair, if we substitute IT here, the tail current by IC, then this is very close to a nanovolt per root hertz. It's actually 900 two times that is 950 or so. Oh, 9255, that's it. 0.9255 nanovolts per root hertz at a milliamp. And again, there's nothing you can do about this. If you want to halve the noise of a differential pair of bipolar transistors, you have to increase the tail current by a factor of 4. Now, that may sound okay if you can spare the current, but it's not okay for another reason, and that is the base current associated with this process as well. And that base current works against the source impedance, and so there's obviously an optimum current at which, for a given source impedance, the noise is minimal. Because as you go up in tail current, this component of noise goes down, but the base current component goes up, being shock noise times the source resistance. So that's all in the notes, so I shouldn't call them notes, I guess. I do have notes for this, but this is these are the slides. And I think I've probably labeled some of these points well enough now to call it quits. Yeah. I'm just wondering if there's something here that's kind of profound and, well, that's sort of profound, but not so profound I'm going to waste any time on it. So we've really only scratched the surface, but what I'm trying to say here is that noise isn't all that hard to understand. Don't be waylaid or not misled so much, but upset by long equations with lots of integral signs and things of that sort. They're all right, they're all useful, they're all correct usually, if all this, all this toast, but they don't get to the root of things. I like to think more intuitively about what's going on, and just, if my equation contains more than about 4 terms and it's high school algebra, then I look for a solution that eventually gets me there. Because in the end, the quantification of these, it's more important to quantify things like noise in a fairly accurate but necessarily imprecise way. You see what I'm saying? That kind of sounds like a disagreement. What I mean is, you want to use accurate methods to get there, and reliable methods, but you don't care too much if you end up with exactly the right number. You just want to say, this is better than that. And oh, here's a way that's bound to be noisy because of this, that, or the other thing. And end up with this intuitive grasp of circuits. Anyway, I appreciate you coming. I hope you can come along to this afternoon's talk, which is much more jovial, much more a sort of a historical journey through a whole bunch of interesting devices going back to World War II. And I think because my throat is gradually telling me that it's time to stop, I will stop. And thank you once again. I guess we're all going to have some lunch. Okay, thanks. If there are questions, this is a good time to ask them. Sort of. Some of the time. Unless
We have time for some
real-
questions
real
if you,
anxious to get to the If non-complicated, come, no. Get. Oh, you've got a question.
Yeah, it's not really important at all. But in this class and the 10th sensors class, I've often heard fractions such as like KT on Q, KT on C. I've never heard of the like on Q or on thing before. It's always been over it.
Yeah.
Do you know where that comes from? Is that like,
It saves a syllable.
I
You say KT on Q enough, but
yeah.
Yeah, well,
Is it a British American
say
thing?
five.
Is it maybe a British American thing?
I don't know.
Say bye.
Yeah, I don't know.
Bye.
As long as you understand where the slash is.
Yeah.
Sometimes